Hello and welcome to this fifth class on special relativity. In the last class, we saw how the special relativity dictionary or transformations imply a whole host of strange effects that were completely unprecedented. The relativity of time, time dilation, moving clocks appearing to tick slower, length contraction, moving rods appearing to be shorter, and the phase offset that we would expect to see in moving clocks. These effects are completely strange, yet today we will see how all of these follow just from the simple additional postulate in special relativity that the speed of light is the same as measured by all inertial observers. The next thing that we will do is expand upon our dictionary for times and positions and include more words in this dictionary. We will include the transformation for velocities and accelerations. Now, in the last class, I only talked about what happens to clocks which are arranged in the direction of motion and what happens to rods which are placed along the direction of motion. We will talk first about what happens to clocks which are arranged perpendicular to the direction of relative motion and rods which are perpendicular to the direction of relative motion. Now let's perform a thought experiment. Let's suppose that we're in a particular frame of reference S. In our previous example, this is, let's say, the platform. And let's consider two events that occur at so we'll set up our coordinate system. So let's suppose this is the x direction, this is the y direction. And now let's suppose that we have an event, and let's suppose we're sitting at the origin. Let's suppose that we detect two events at the same time t, and these events are seen at location y1 on the y-axis, and another location, let's say minus y1 on the y-axis. Now, one way we can tell these are simultaneous, even if we haven't checked our synchronized clocks, is to send light signals. And if we're sitting at the midpoint between these two events, then we will see the light signals from these events reach us simultaneously. So now the question is, if these two events appear simultaneous to us, do they also appear to be simultaneous to an observer who is moving along the x direction? Okay, so now consider a frame S prime, and in this frame S prime is moving to the right at a speed v along the x direction. And we want to know if the events which occurred at coordinates 0, y1 and 0, minus y1 appear to be simultaneous to in the frame S, do they appear to also be simultaneous in the frame S prime? We previously saw that if the observer is traveling in the same direction, that is, if the observer S prime was traveling in the y direction, these events would not appear to be simultaneous to observers on a train, say. Okay, but what about if these events are occurring at the same spatial coordinate, but the direction of motion is perpendicular to, if they're occurring at the same x coordinate, but the direction of motion is in the x direction. Now we can easily visualize what will happen. So imagine that O prime passes O at the same instant t at which these events occur, and O prime then continues to go further ahead. Okay, so after some time delta t, they would have moved a distance of v delta t along the x-axis. And now if you also imagine that O prime had some friends who passed the events which were at y1 and minus y1, these friends would send light signals to O prime. Now, these light signals would travel at the speed of light and eventually they would reach observer O prime. Okay, and these signals would traverse exactly the same distance as seen by observer S on the ground, and therefore observer S would conclude that these two events, these two signals, reach observer O prime simultaneously. Okay, so there is no reason that S prime should also not see these events to be simultaneous. So to conclude, if we have motion of S prime perpendicular to two simultaneous events, or if we have two clocks as seen by the ground observer, that are simultaneous, if the ground observer simultaneously peeks into the clocks of the train observer, these clocks might show different times. So, for example, they show a different time here, but they will be in phase with each other. Okay, so that is, these events which are in the perpendicular direction will appear to be simultaneous, as seen by observer S prime. So as long as S prime is moving perpendicular to these clocks, those clocks will appear to be in sync or synchronized with each other in perpendicular directions to the direction of motion. Okay, so let's write that down. Clocks perpendicular, or clocks placed perpendicular to the direction of relative motion do not have a phase offset. Okay, and we can also see this explicitly from the special relativity transformations. If the motion is only along the x direction, then t prime is, we saw it's gamma times t minus vx over c square, where gamma is 1 over the square root of 1 minus v square by c square. So the new time coordinate, that is the time coordinate as measured in the frame S prime, depends only on the old time coordinates, t, and the x coordinate x, which is the same for both these clocks, and therefore the time t prime on the moving clocks would be the same. Okay, these clocks would agree with each other. They may not agree with the clocks on the ground, and we know that they will tick at different rates from the clocks on the ground, but these clocks will appear to be to have no phase offset from each other.